Thanks for the invitation. I want first to say that it is a great pleasure and honor to celebrate Toshiyuki's 60th birthday. I mean, the breaking symmetries of representation in particular have always seems to me an impossible problem. So I was always very impressed by his work on discrete breaking symmetry for cohomological modules. So of course it had impacted a lot of field that is very important to, that I love particularly, that of cohomology of locally symmetric spaces. So I decided to give a talk on that subject, though it will be much more elementary. So I will talk on homology torsion growth. So it's harder to capture through analytical methods. So I will use mostly very soft tools. But first, let me state the problem and start with, before even talking about homology, with a simple question about just abelianization, which most of you must know that it's related to H1. But let's just take a group, gamma, and recall that its abelianization is the quotient by the commutator, and in that way you get a Z module, and as such you can decompose it as a free part and a torsion part. And I want to first consider a certain type of example that seems very close but have different behavior. So consider a ring R and the matrix in SL2 of R, and that are A, B, C, D, and ask that let's say C is divided by some element n in R. So then you get a group, and the link with homology that I will discuss later is that the abelianization of this group, the abelianization of this group is exactly the first homology group, but let's forget about it right now. I want to say to understand the structure of this abelianization, and we will see that it's quite different depending on the choice of the ring R. So let's consider the very well-known case where R is just the integer. Then gamma naught of n is so-called congruent subgroup of SL2Z. It acts properly discontinuously on the Poincaré apparat plane, and the quotient is a Riemann surface, a hyperbolic surface of finite area. And the question is of the free understanding the free part of the abelianization is the same as understanding as I said, the cohomology, or it's also the same as understanding somehow the number of modular form of level n and weight 2. And in that case, this is well understood and completely controlled by the area of the surface, and there is essentially no torsion part in this abelianization. So the Z module abelianization of gamma naught of n has essentially no torsion. I'm a bit cheating here, and it has a free part, which is essentially the same as a number of weight of level n weight 2 modular form. So it's something quite interesting, but no torsion. So related to the title of this work, there is nothing to say very interesting here. Let's consider another case, for example, the case where R is a ring of integer of a real quadratic field. So you can think of R as a Z of square root of D, where D is positive. Then in that case, the picture is even simpler. Is simpler. The abelianization is finite, and it's a small group. And this is related to an interesting feature of OD. It's related to the fact that OD, being the ring of integer of a real quadratic field, has infinitely many units. And you can use these units to produce a big commutator group. For example, just to give you a reason why the abelianization is finite, if you take a unit in OD, then you can form the matrix, the diagonal matrix U minus 1, and take the commutator with the unipotent matrix Y, which is 1, 1, 0, 1. These two elements belongs to gamma naught of n, and if you form the commutator, you get more elements thanks to U. You take more unipotent elements. So the commutator subgroup is in fact quite big, and playing like that, you can, in the end, even show that the abelianization of gamma naught of n is finite. So here there is very few homology. Let's say that it's not very interesting in degree 1. And now let's consider the case of imaginary quadratic field. So now you can think of R Z of square root of D, but D is the negative. Then the group of units is finite, so we cannot play the same game. And in fact, it was already noticed more than 35 years ago by Elstrode, Grunwald, and Mennike by computing some examples that as n grows, it seems that the finitely generated Z module, which is the abelianization of gamma naught of n, they tend to have a free part of small rank, but a torsion part of large size. It took some time to realize that, because you have to let n grow a little bit to start seeing something. Here, just to give you some example, I will show you some more recent computations by Alok Sengun. And the computations are made in the case of Z of I, so D is minus 1. And you will see in the computation, the first entry is the norm of the level n. You consider levels that can be ideal, so in fact that are prime ideal. So you will see norms that are primes, and then the sequence of number. The first number will be the size of the free part, and the other number will be the prime divisors of the torsion part of the abelianization of gamma naught of n. So let's consider. So for example, the first case. The prime is a divisor of 5. The first 0 says that there is no free part in the homology, and the torsion part is just Z mod 2Z. And so we can play like that with bigger and bigger prime. So as you can see, looking at the first column, the free part is quite small. I mean, the biggest in this column, the biggest in this number is 2. So there is quite whereas the level is already quite large. So the free part is quite small. But letting n grow bigger, we see more and more prime in the torsion part. The most striking case may be this one. Where you start seeing quite big primes. So the size of the torsion, of course, is the product of this prime numbers, and you can go deeper and deeper, and you see that level that is big but not that big. You start seeing very big primes in the. You still have no free part, but you see a lot of big primes in the torsion. So the torsion seems to be interesting in containing a lot of prime divisors, and so it's tempting to try to say anything on that question, and to wonder when torsion is big and so on. So that's what I I want to discuss today. Let me first state a conjecture related to this question. So the group we were considering are subgroup of SL2 of OD, because the ring was OD, where D is negative. And these groups are called Bianchi groups, and they are discrete subgroup of SL2C. And as such, they ask on the locally symmetric space associated to on the symmetric space associated to SL2C, which is the hyperbolic tree space. So the analog of the fundamental domain of the modular group on the Poincare upper half plane is the picture here, where you see a fundamental domain of a Bianchi group acting on the hyperbolic tree space. And as in the case of the modular group, the first way to measure complexity of this Bianchi group is to measure the volume of the quotient, or the volume of a fundamental domain. And the question you can ask then is, in terms of the volume, if you bound the volume, can you bound the topological complexity, and for example, the homology, the torsion homology of the manifold? What can be said about the topology of the manifold if you control the volume? That's a question that is studied a lot for homology in general locally symmetric space. There is a whole book by Ballman, Gromov, and Schroeder on that subject. So can you bound the Betti numbers if you bound the volume of this quotient? And so here I'm sticking to the hyperbolic tree space. The quotient has finite volume. As I said, we have the volume that this volume measures the complexity of the lattice. And the question is, what can we say? What can we say about the topology? And with Akshay Venkatesh, when the manifold are arithmetic, so let's stick to the sequence of example I was discussing up to now. Then you have this sequence that depends on capital N, and the manifold becomes more and more complicated. The volume tends to infinity. So you are exactly in the setting where you have a sequence of congruence hyperbolic tree manifolds such that the volume tends to infinity. And you ask, what can you say about the torsion? And the conjecture is that if you take the log of the torsion in H1 and you divide by the volume, then it tends to a positive constant, which we conjecture to be 1/6 pi. So in other words, 1/6 pi is quite small, but so that's why it took some time before noticing there is quite a lot of torsion. But the torsion grows exponentially in terms of the volume of the manifold. So if the volume is big enough, we expect to see a lot of torsion. And if you look at the computation by Sengun, you see that it's completely coherent with that. You see a number that is close to 1/6 pi when you compute this ratio of log of torsion divided by the volume. So that's one conjecture that is still very open, but in fact it sits in a bigger there is a bigger conjecture that involves more locally symmetric spaces, and but for that you have to consider a higher homology, not only H1. So now let me go to the same question but for more groups and about higher homology. So now, given a group, you can consider not only the homology of the Abelianization, but you can consider the homology in any degree and with Z coefficient, and you still have a decomposition of this Z module as a free part, where the rank of the free part is exactly the Betti number of the degree G of gamma. And you have a torsion part, which I want to discuss today. And the case I want to consider are finite index subgroup of SL and Z instead of considering the ring like imaginary, like ring the algebraic, I mean, more complicated algebraic numbers like totally imaginary quadratic field. I can just consider Z, but I take a bigger group by taking SLN. And in that setting, we have a similar conjecture about the growth of torsion homology. So you can consider a sequence of finite index subgroup of SL and Z, for example, a congruent subgroup. But take any sequence of finite index subgroup of SL and Z, and consider the homology, let's say in degree Q, of these groups, and consider the torsion part, the size of the torsion part, take the logarithm and divide by what captures essentially what captures the volume up to a constant, which is the index of gamma I inside SL and Z. And the conjecture is that in most cases, the torsion will be sub-exponential, so the quotient will tend to 0, unless in two particularly interesting cases, the case where n equals 3, so SL3, and the degree is 2. In that case, here again, we expect to see exponential growth of torsion, but the constant in the exponential will be quite small, as you see, and it's even worse in the case n equals 4 and q equals 4. This is the other case where we expect to see exponential growth of torsion, and the constant is even smaller. So I think it was quite a surprise to see as many, to expect to see as many torsion in these two cases. And the reason is that to get first example with torsion, you have to go quite high in the level. You have to take small gamma I because these constants are very small. But once we made this conjecture, then Gunnell, Siazaki, and sorry, I forgot the other authors, were able to compute numerically the homology in higher level, and they managed to see that we see exponential torsion growth with a constant that is compatible with these numbers. So in that sequence, we expect a lot of torsion, but in all of the degrees, we expect few torsion, and quite surprisingly, it's not easy either to bound the torsion to show that it's sub-exponential. And so today I will discuss this apparently simpler question and explain the proof of the following theorem that we got with Miklos Abert, Damien Gaborio, and Nicolas Bergeron. So take, as I said above, gamma to be SL and Z. Take n bigger than 3, and consider a sequence of pairwise different finite index subgroup of gamma. So you think of a sequence of subgroup, and that is smaller and smaller. So the volume of the quotient becomes bigger and bigger, or the index gamma I tends to infinity. Then, in small degree, up to degree n-2, the torsion is really sub-exponential with respect to the index. So it's that's the theorem I want to discuss. Let me first say that the first case of this theorem is a case where Q is equal to 1. So the case of the abelianization. Then it's well known from a long time that there is no free part in the homology. but you can still wonder, is there a torsion, is there a lot of torsion or not? And in fact, this case, it was already known that this is sub-exponential. And in fact, if you look at, if you use a congruent subgroup property, you can even have a very strong bound on the torsion homology. The torsion homology is a polynomial, is at most polynomial in the index. So it's not trivial in general, but it's very far from being exponential in the index. It's polynomial, and the proof only works for degree 1 because it uses works on the congruent subgroup property, and it's much higher. At least I don't know how to push this kind of methods to work on higher degree homology. Now, what was known before? I mean, there is a bound on the torsion, on the size of the torsion, which I want to call a trivial bound. So the proof is not that trivial, but this is the limit bound of in the question, and this is precisely that the size of the torsion is sub-exponential with respect to the index. So if you take a torsion-free finite index subgroup of SLNZ, then the log of the torsion part of the homology in any degree is bigger, bounded up to a constant that depends only on n by the index of gamma in SLNZ. So the trivial bound, the bound that you get in the first attempt to bound the torsion part, is precisely the exponential bound, and the goal of the theorem is to go beyond this trivial bound. So let me explain roughly what is the idea behind this bound. This is really just a sketch. But there is a nice lemma of that I think the first to mention this lemma was Hofer-Gaber, which says that if you, so this is a very general lemma. It's concerned with any gamma if you want, but the log of the torsion homology of gamma. So if you think of the usual homology of gamma, since you can compute it with any complex finite complex that computes the homology, then if you bound the number of cells in the complex, you will have bound on the Betti numbers on the homology. For the torsion part, it's a little bit harder, but if you know how to bound it's not J here, it's Q. But if you know how to bound the number of cells in a CW complex that computes the homology of gamma, if you know how to bound the number of Q cells, and if you know to bound the log of the L2 norm of the boundary map, then you have enough information to bound the log of torsion. So there is a way, a combinatorial way to bound the torsion. You just have to fix. You have to have enough information on the chain on the CW complex that computes the homology of gamma. So, but what I want you to remember is that you need information on the number of cells and on the in the degree we are considering, and on the boundary operator from the degree above, just above. So that's a classical. Classical. No, that's a result that was well known on the if you want to study torsion homology. And now you wonder, how can you use it, apply it to subgroup of gamma? And for that you can use a theorem of Gelander that says that if you fix n, there exists a positive constant, and a CW complex that computes the homotopy to K gamma 1, and that has as most the index of gamma into SLNZ times this constant beta cells in each dimension. So you have a complete you bound completely in any degree the number of cells you need. And with this theorem and the lemma of Gaber, then you have a way to bound the log of the torsion, and the bound you get is something that only involves the degree, the index of gamma in SLNZ, and that's how you get the trivial bound that I don't like to call trivial because there is quite a lot of math already to prove it, but it's the rough bound, if you want. And now the whole game is to try to understand better the structure of a cell complex that computes the homology of gamma, to be able to go beyond this bound, at least in some degrees. And that's what I want to discuss in the rest of the talk, to go beyond this trivial bound. And for that, the tool, as I try to explain, is to find good CW complex to understand the topology of gamma. So of course, the first thing we can do, we know that gamma acts on the symmetric space associated to the symmetric space associated to SLN, and we could try to decompose to find a fundamental domain for this action and look at how many cells of this fundamental domain and so on. But the thing is that if you take SLN, the fundamental domain, and pass to finite index subgroup, then it will be a nightmare to understand the combinatorics of this CW complex. So what we can do is relax a bit what we ask on the space on which act gamma, and let it act on a CW complex, but not freely. So that we will lose some information, but maybe we will understand better the structure of the CW complex. And so the way to do this is to use the so-called Borel construction. So the general setting is the following: you take gamma to be a countable group acting on a CW complex omega, and let's suppose that omega is nice up to a degree alpha. Nice being meaning that it is omega is alpha connected. It's not contractible, but it's alpha connected up to. It's alpha connected, and now you have this action of gamma, but you don't require the action to be free. So there will be stabilizers of some point we'll have stabilizers, and from this data we want to construct a CW complex which understand completely the homology of gamma, at least up to degree alpha. So we want to construct an alpha aspherical CW complex whose fundamental group will be gamma. And the way we do that it's called a stack of CW complex. We have the quotient omega by gamma, which is not so nice because gamma doesn't act freely, but over each cell in omega mod gamma, we take, like in the fiber bundle, we glue classifying space for the stabilizer. So this space is the classifying space for the stabilizer, and so the space sigma, which is given by Borel construction, is kind of it's not a fiber bundle, but it's kind of that. It's a stack, and the base is omega over gamma, and over each point you see something which is a classifying space for the stabilizer gamma of gamma omega of omega. So we have. If you want, we will start with an action we understand pretty well, except that there are stabilizer, and we will put the stabilizer a bit arbitrarily by taking some classifying space to get a complex that is harder to understand, but it's still decomposed as something that projects onto a quotient that we understand, and the fibers are only involve smaller subgroups of gamma that are the stabilizer of the point omega. So to make things, to explain what will be the omega in our setting, let me say immediately that the complex we will use is a so-called rational Tits building. So it's a way to compactify the symmetric space associated to SLN. This is a complex that is n-3 connected, and the stabilizer of the point in omega for the action of gamma on the Tits building, they all contain so there are parabolic subgroup. And they all contain the non-trivial free abelian normal subgroup. So these stabilizer are the space you associate to this stabilizer are torus bundle, and this torus bundle will be much easier to modify, to simplify the number of cells you need to understand the complete space sigma that computes the topology of gamma. So in that way, we want to build nicer classifying space for finite index subgroup by using the structure of the stabilizer of the points that have the advantage to contain the free abelian normal subgroups. So that will be the idea of the proof. And now at the end, using the same lemma, the lemma of Gaber, to estimate torsion homology, we need to bound the number of cells that we are using and the norms of the boundary map. So we have to be quite cautious. To follow exactly what modification we do on the cellular complex to control the number of cells and the norms of the boundary map. And so that's the motivation to introduce the next important step in the proof is the notion of rebuilding. The notion of rebuilding, so I will review what is written here, but it's a natural notion. We have a cellular complex X at the beginning that we know computes the homology of gamma at least up to a degree alpha, and we want to modify it so that it has a smaller skeleton, so less cells. And that's what we will call a rebuilding. But we want to remember, in the end, we will need to remember also what are the boundary map and so on. So we have to remember the homotopy, the two cellular maps that are homotopy inverse between X and X prime. So the data is the following. You have a CW complex X, which is a finite CW complex, at least up to dimension alpha. And so a rebuilding is another finite, is another CW complex with finite skeleton up to degree alpha. and two cellular maps between the alpha skeletons, and the homotopy. So the two cellular maps are just here to say that the two complexes are homotopy inverse up to degree alpha, but we have to remember the map and to remember how we pass from one to the other. We have to remember the homotopy at least up to degree alpha minus 1. So again, the philosophy is that we want to simplify the cellular complex to have a smaller skeleton, and we want to remember to remember the quality of this simplification, and that's why we bound the quality of such a rebuilding. And the quality depends on two numbers, T and kappa. And so we ask that the number of cells in the rebuilded cellular complex is the number of cells of the first cellular complex, but divided by T. And there is we authorize some kappa constant for the. You can, for the moment, you can a bit forget about the kappa. I have to put it, but it's not that important. But the important is that this T allows to diminish the number of cells. So that would be enough to bound Betti numbers. But we've seen that for the torsion, we also need to bound the boundary map in the new complex. And for that, we need to bound all the logs of these. So these are the maps associated to the homotopy equivalence between x and x prime. This is the chain homotopy, and this is the boundary map. And so we ask that these logs are bounded by 1 plus log t. So again, we want to have few cells, but the norms of the boundary operator and all the cellular maps that are involved in this, we want them to have a small, to remain, to have a norm that are controlled, and in the sense that the log of their norms should be controlled roughly by the log of t. So that's a way to measure the quality of a rebuilding. And now the goal is to find a rebuilding with few cells and norm and still a good norm bound. So I can now explain how to go toward the theorem in that way. So think of X as obtained in the as a cellular complex that computes the homology, and take a finite cover associated to gamma, to a finite index subgroup in a cell NZ. And now the goal is to rebuild the finite cover X1 with sufficiently good quality. So small number of cells and control on the boundary. So in some cases, and it's possible to forget about kappa essentially, and to take T1, which is the quality of the rebuilding, to be linear in the degree. The cases you can have in mind, the most basic cases, is the case of a circle. If you have a circle and take a finite cover of degree n of the circle, then you see that the number of cells you need to the number of cells of the cover is the degree of the cover. So when you pass to a circle with, let's say, one vertex and one edge, so just a circle as the quotient of an interval by the two extremities, and you pass to degree n cover, then you will have n1 cells and n vertices. So it's too much, but what you can do is just replace this cellulation by taking only one 0 cell and one big edge, and in that way you have a very good quality rebuilding on the circle. And in fact, somehow all the proof will be to reduce progressively to this simple case, using that there is a lot of circles in this situation. So let me say that this is the most basic case where it's easy to rebuild, and let me explain how we reduce to this case. And so that's the sentence here. To prove the theorem, we will use the fact that when you take this finite index subgroup gamma I in SL and Z, then they intersect most of the infinite unipotent subgroup. So take triangular subgroup which in SL and Z, and they will intersect most of them, conjugate of them, along subgroup of large index. So you will see a lot of, in the torus bundle I was mentioning in the beginning, you will see lots of big torus that could be simplified a lot, because you replace a complete triangulation of the torus by a much simpler one, where you take only essentially one cell in each dimension. So that's the way we proceed, and the way to formalize this is a property that we call the cheap rebuilding property that I kind of find interesting, and that concerns a lot of group. You can take any general residually finite group. We want to capture when we can rebuild easily the classifying space for finite index subgroup of gamma. So we will say that gamma has a cheap alpha rebuilding property. If you can find a classifying space for X for gamma, which has finite skeleton up to degree alpha, and you can find also a constant, kappa X that only depends on X, and so that you have the following property. If you take any, I will define what it is, any Farber sequence gamma I. So in first contribution, you can just think that gamma I is a sequence of subgroup, of finite index subgroup, and we don't want to consider only normal subgroup because it's too much to ask. But let's say for the moment that it's a normal subgroup, then we will ask that the intersection of the gamma I is trivial, is a trivial group. In general, we don't ask this, but we say that the group is not far from being normal and of index tending to infinity. So it means that the number of fixed points of a non-trivial element in gamma on the quotient gamma over gamma I, which will be 0 if gamma I will be normal. But we just ask that this number of fixed points is quite small compared to the index. It tends to 0 when you compare to the index. So you can think of it as not far from being a sequence of normal subgroup whose index tends to infinity. The intersection is trivial at some point. So we want subgroup that looks more that are bigger and that are smaller and smaller in gamma, so that the quotient looks more and more like the symmetric space. So for any Farber sequence like that, and for any T, we want that there exists some index such that above this index, the quotient the corresponding finite index cover xi of x associated to gamma I admits an alpha rebuilding of good quality, t. So if you go for any t, if you go far away in the sequence, then you can find a rebuilding of quality t. So you can really find small, much a cellulation which much less cells, and nevertheless you control the boundary. So that says something quite interesting, I think, on the group. If it exists, and you of course it depends on alpha. You can consider only the up to cohomology degree 1 or 2 or etc. And what we the technique of our proof is to explain how to bootstrap this property from a smaller group to bigger group. So and the theorem we prove is typically is something like that. Coming back to the construction where gamma acts on the space omega with stabilizer. Suppose that the quotient omega mod gamma, so you can think of it as a teeth building quotiented by SLNZ, but of course there are other possible situations. Suppose that it has finite alpha skeleton, that omega is highly connected, alpha minus 1 connected. So these are really basic things, and now you ask that you have something on the stabilizer. You have to ask the stabilizer to have some property to be able to bootstrap this. And here you ask that the stabilizer of a cell of a dimension j, less than alpha, has the cheap alpha minus j rebuilding property. So you know to rebuild the fiber up to a certain degree. Again, you have to think that, let's say the fiber will be circles, then this fiber, you know how to diminish the number of cells you need to understand the homology. And so by rebuilding this circle, you find a rebuilding of the whole sigma, the Borel construction associated to gamma acting on omega. And from that, you get the cheap rebuilding of gamma. So from this data and condition just on the stabilizer of the vertex, you get something on the group gamma. So here are some corollary. So for example, having this property is an invariant of commensurability, but more importantly, if you have a normal subgroup n inside gamma, and if n has the cheap rebuilding property in degree, the cheap alpha rebuilding property, and the quotient gamma mod n is relatively nice as a finite cohomological dimension, if you want, then the group gamma itself has a cheap alpha rebuilding property. So that's a way to have more and more groups. Typically, you start with you start with a group like Z or an abelian group, and then from that you pass to a parabolic subgroup, and then applying again the same theorem, you get to richer and richer groups, like the one in this theorem. You can get arithmetic lattice with big Q rank like SLNZ, where the Q rank is n minus 1. The Q rank serves to reduce to the to have a big interesting TIDS boundary and to reduce to the stabilizer of to the action on this omega. And I don't want to mention now, but you have also application to Artin groups or mapping class group using the same kind of techniques. And now let's go back to homology growth. Let's put it in the large setting of a countable group of so f alpha plus 1. Let's say it has a finite cohomological dimension in any. I mean, it has. Let's say it's of type f infinity, so it has a finite cohomological dimension, or even that it has finite cohomological dimension. It's not very important, this hypothesis. What is important, it has a cheap alpha rebuilding property for some alpha. Then, if you take any sequence, a Farber sequence, so in particular any sequence of finite subgroup in SLN, a distinct subgroup in SLNZ, then you can bound using this as well the Betti numbers for any coefficient field, or even, which is a bit harder, the torsion, because we control, in the second case, because we control the boundary operator. So in both cases, up to degree alpha, you control completely the homology and the torsion. Now, if you apply this to SLNZ, alpha is equal to n minus n minus 2, and you get the statement in the beginning of that I mentioned in the beginning of the talk. Just to say that if you consider particular finite index subgroup of SLNZ, typically principal congruent subgroup, we can make this more, we can follow more the constant, and then you can really have a better estimate on the growth. So if you consider gamma of n the principal congruent subgroup, then for example, if you look at the torsion, the log of the torsion divided by the index is bounded by log of n divided by n to the n minus 1. So you can really follow the proof and count how much you can decrease the number of cells, etc. We are not expecting that it is a good estimate, as it's very hard to say something about torsion. But if I had to bet something, I would say that in these degrees, the size of the torsion should rather be polynomial than. So we are far from this, but that's what we can do for the moment. And now let me jump to the conclusion. So as I said, vanishing theorems are cool because we don't know much about this, so it's better than the trivial bound. But it's a bit. Of course, the most interesting would be to have examples where the torsion is really exponential growth. Neither of the cases I mentioned in the beginning is known. There is a recent interesting work of Avramidi, Okun, and Shrev, who have constructed example of some particular right-angle Artin group where they can get exponential growth of torsion in degree 2. So it was the first case where there are towers where the torsion grows exponentially. But what is quite frustrating, and I want to advertise this because it's very frustrating that we have no example like that. As I said in the beginning, for Bianchi groups, we expect that the H1 is should be the torsion in the H1 should be exponential in the degree. But in fact, we don't know to prove that. But in fact, we don't know any group gamma, finitely presented group gamma, and the Ferber sequence in that group. So, for example, a sequence of finite index normal subgroup with trivial intersection, such that the log of the torsion in the abelianization or in the H1 is really exponential with respect to the index. So that's, I find, a very frustrating question. So I wanted to end with that, and hopefully someone here will show me an example at some point. Thanks.